Okay, so now that we have our circuit diagram built, it's time to go ahead and attach the footprints. Now, if I pull this assignment back up here, it gives us the particular footprints that we're supposed to use. Now, again, these are our built-in footprints, and let me just go ahead and show you, because if you're ever on one of the computers in the computer lab, you can actually go and see the footprints this way as well. If you go to where cadence is, well, currently we have the 17.2, but we will be upgrading to 17.4, but it's in the same location for both of them. Go 17.2, you go to share, you go to PCB, PCB lib, which is library, and then symbols. And then these are all their symbols. So for instance, if I just pull up one of them here, I'll just do the SMR. So we have the 1206 here. Let me pull up the drawing here. So this is the SMRC 1206 footprint, and this is actually a footprint for a surface mount component. It's a surface mount resistor, and 1206 has to do with the size of it. And just here to kind of give you an idea of the size of things here, Hicks footprint. Let's see if this one gives it here. This might be the table I'm looking for. No, that's just the actual dimensions. So this is dimensions in millimeters, 3.2 millimeters. And this is actually still a relatively large component here. So let me see if I can do resistor, surface mount resistor sizes. See if it actually, yeah, here we go. This one is, I think, a decent picture. There's that one. This one's even better. Well, except it's all gray. I don't want to go there, it's boring me. But you can kind of see here. So this is a DIP package, dual inline package. Here's a 1206 resistor. There's 805, there's 603, and then there's a 102. And trying to solder a 102 by hand is, I would say, almost impossible. I'm not saying you couldn't do it, but there's a reason why you have those automated machines that you saw that assemble those boards. So we're going to be doing the 1206 just purely because you can get resistors in that size, and that as far as if you were to ever solder by hand, that's the size you'd use. Now, as far as how do you pick the size of resistor normally for a layout, well, often that's not necessarily picked for you because it's not a decision you make, because there will be a specific part number associated with each resistor, and that part number will tell you what the footprint is. So that the part number will say, oh, well, that's a 201 package, or the part number will say, oh, that's a 1206 package. So you'll know that way. But in this case, we're using SMR 1206. So let me go ahead and do the same thing I did here before, so we can see both things here. So all of my resistors, so let me first do the Control A, so I'm going to select everything, and then I'm going to right click and do Edit Properties, and then I'm going to go to Parts, and then again, with the way I have mine set, I have the PCB footprint here because I have the things where it's the parts listed across the top and the properties listed down here in the first column. If yours doesn't look like that, remember there's this pivot, and then here this would be the parts being listed, and then these are the properties. And so you can hit pivot again to have it in either display, and this is again just the display that I prefer. And so, well, the first ones here are these capacitors. So the capacitors are SMC 1206, And then I'll just copy and paste that. And then these are diodes. These are the D1N4148. So if I go here and go to the next one, D1 and D2, that is SOD 87. And then this is J1 and J2. In the diagram it said J2 and J3. That's just because of how it was labeled in the diagram. But when we placed it, this was called J1 and this one was called J2. I'll just go back to the schematic. See, this was called J1, this one was called J2, corresponds to J2 and J3. And so those footprints were, actually that's a typo there. It should not be header 2, and R1 shouldn't be header 3. These should be jumper 2. So that was a mistake in the assignment that I had made a long time ago. So jumper 2. Oops, I don't know what happened there. No, I don't want to delete the property. Or maybe did I add a new property? I don't know what I did here. Let's go ahead and delete this property. Oh, it says I'm not allowed to. Let's just close this tab out and then get back in there. I don't know, I got into some menu area that I have no idea where that was. Okay, so let's get back to my footprints. Jumper 2. And then this here, Q1, that's the transistor. And that is SOT23 that we're going to use. The variable resistor, again, that was mislabeled. That should be jumper 3, not header 3. So there was a mistake in the document. That would have been terrible for students. And then we have some other resistors, SMR 1206. Okay. So now I've put all of the parts in there. I'm going to close this out. I'm going to go ahead and do a save on it. And then I don't need this document anymore right now, so I'll maximize this screen. And then I've saved it, I've got all my footprints, and then that's when I go to this DSN file and I do annotate. And we say OK. And then we go to create netlist. And then it says there's no Allegro directory. Do you want to create one? Yes. Now I have an error. Ooh. In fact, I'm glad I have an error because that means this is something that you sometimes get. Oh, property PCB footprint missing from instance U1. Okay, aborting Netlist. So I forgot to attach a footprint to something, and that's this chip right here. But if I just go ahead and select everything again, it said U1, so I know it's this chip, but I'll just select everything again. And I can go back through my PCB footprints, and I can see that, yeah, for some reason, you guys were probably all, if you're watching the video, you're like, well, why'd you leave that one blank? Yeah, I forgot to put a footprint in there for U1. And so if I go here, that one was the 555 alt is SOIC8. So even someone who's been doing this for a long time can still make mistakes. Now, you technically probably don't need to re-annotate it, but I'm going to still do that anyway. And then export, not export, create netlist. And now that time I didn't get an error and it was successfully done, and I have my output files here from my Netlist. Okay, so let's go ahead and get started on doing the actual layout here. So I had opened this program to show you the footprint there. And so I'm going to go ahead and just do a file, new, not going to save it, and then package symbol wizard. And then currently I'm in the symbols directory. I wouldn't want to save it. I want to go again. Usually the best way to do this is to go to the directory that you are saving this in. So this is an ECE 1000, assignment 10. And I've actually failed to do things here. So this is assignment 10 folder, but I think, let me see, go back and actually see where these things got saved. Yeah, you see, I wasn't careful on where I saved everything. I must have not been careful when I selected my directory, and it actually didn't put everything in there. And so I can see the Allegro directory that it saved the Netlist files in is ECE Allegro. So that's where I'm going to want to browse to, ECE 1000 Allegro. And then I'm just going to call this assignment 10. But what that shows you here, and let me go back and show you again, if you can't find what the directory is here, what I did here is I say, wait a minute, I can't figure out what directory the Netlist files were saved in. I just went to tools, like I was going to netlist it again, and then for the Netlist files here, you could change the directory, but I just went ahead and looked up, and apparently now it is being silly on me, because you all saw it last time where it actually showed you the directory that it was in, but now it's probably wanting me to, it's thinking I'm trying to change directory, but this is the directory it was in. And if we want to just be safe, I could always just re-netlist it again. And there was yeah, so it did it again. Where did my board wizard thing go to? My PCB editor just died on me somehow, or I exited out of it. It must be a Friday. So new board wizard, browse the directory. We're not going to be in my download directory. And hey, you can also see, if you've been paying attention, I'm getting on sidetracks here, but hey, yeah, I play Blizzard games, I play Dragon Age, or I did, back in the day, Mass Effect, all those old school games. I play newer games too, but yeah. ECE 1000. Wait, I'm in the wrong area. No, actually what I did is I saved it into a different area. I saved it, what am I talking about? I did save it here. And then I'm going to just say assignment 10. But now instead of saving it in my OneDrive account, I'm saving it actually on my computer, on my magnetic hard drive, my D drive. So we'll go through here. Now, we're going to do something a little bit different on this one here. You know how we've been doing everything in millimeters? Let's go ahead and leave it at mils. It's okay to have it at mils, even if a lot of other things are in millimeters, but we'll go ahead and leave that. Now, grid spacing is 1 mil, so that's 1,000th of an inch. Now, I'm going to go ahead and leave it at that, just to show you what happens when you leave the grid spacing that fine, because there's no reason to not have it that fine, but I'll show you what happens with it. So I'll do next. And I accidentally double clicked, which is why that error came up to me. Now, minimum line width. So this is actually what we're going to do here. I'm going to show you something, is trace width based on current. And so you can see I've already opened a bunch of these calculators. I was looking at the different ones here. But what's interesting here is you might say that, okay, you know, this one's using formulas from IPC 2221, which actually is okay. But then there's, you know, some other ones here. I like the DigiKey one, mainly because I go to DigiKey for everything, and you know, it's using the formulas from IPC 2221. And there's a lot of different information you have to enter here. So you have to enter basically the current, and what you're wanting to know is what's the maximum current that's going to be going through these traces. Now, these traces in general are going to be pretty low current, but if I look here, the maximum current is really going to be here for driving and that, how do you know that? I just know that because I've experienced with the circuit. You would know that once you've been through courses. And a back of the envelope computation that's not going to be 100% accurate, but it gives us at least a ballpark. We would say, okay, what's our power supply? 12 volts divided by 330 ohms. So 36.3 milliamps, or 0.04 amps. And so I'll just show you what happens here when you do something like that. 0.04 amps. Thickness of my copper, we have 1 ounce copper that we use here. Typically it comes in 1 ounce or 2 ounces. They used to have half-ounce copper. It's not as typical to find anymore, so we have 1 ounce copper is what we use here. Now, temperature rise, like how much is the device going to heat up? What's the temperature rise going to be? Now, there's not going to be a lot of heat in here, so you know, you don't want to enter 0, but you know, if you want to be safe, you could say, okay, well, there's a 30 degrees Celsius temperature rise. That's a pretty significant temperature rise. If you figure that's covering essentially, you know, freezing to room temperature if you were to convert that to Fahrenheit. You know, so you know that's pretty thing. Ambient temperature 25 degrees Celsius. That's a little warm for ambient temperature. So, but that's not an unreasonable. Now, trace length, like, well, how long could possibly one of these traces be? So, you know, and you can see right here, we don't have it, and we're at 0.18 mils. So not even 1 mil width here. So if I say, let's say 12 inches is my trace width, you know, that's just computing the resistance and the voltage drop for me and the power loss. But if I say it's like, oh, well, it's going to be 0.1 inches, well, then you can see voltage drop, you know, and everything. But then again, the minimum trace width is 0.18 mils. And so let me just show you, if I put in 1 amp, oh, well, now that's saying I need 15 mils of a trace width. But also notice that the resistance has gone down as well, so your voltage drop has gone way down. And so if I went to a 12 inch, you know, there's not nearly as much voltage drop going on. And you know, you can kind of play with this calculator. You can say 2 amps. Okay, well, now we need a 41 mil trace width. But let's just go to the 1 amp, because that's going to be plenty. And so it's basically 15.7 mils. Now again, if you were to be at 2 ounce copper, not surprisingly, it's roughly half. You know, but we're going to be at 1 ounce copper. So we'll actually go ahead and go back to our program, and set this minimum line width to be 16 mils. And we'll go ahead and leave the pad to pad spacing and everything else to be 16 mils as well. And then we'll use the default pad stack of Avia. And then again, for some reason it always wants us to make a circular board, but we'll make a rectangular board. And then this is in mils, so that's 1 inch by 1 inch. So let's go ahead and just make it plenty big, just for so we have plenty of space. You know, we're not going to worry about any physical constraints at this point for it. So we'll just make this 8 inches by 8 inches, which is way big. But then let's go ahead and do a corner cutoff, just so you can see what happens when you do it. So let's do a corner cutoff of, let's say, 500 mils. And then a route keep-in distance of 500. Well, let's actually just leave those as 0, just because we're going to say we can go all the way to the edge of the board. And so you don't see those other lines like how we had in the other examples, those multiple colors, because we're saying the package and keep-in and the route keep-in are basically the same here. But you can see now these nice little cut-ins that we have going on here. So that's kind of nice, just being able to see the cut-ins. And so let's go ahead and do our next step, which is importing our netlist. And so we're going to do capture CIS. And now the import directory, that is where my netlist files are stored. I'm already in there, so it's processing. It said completing with warnings or errors. Oh, it said all of these things are not found in my PSM path, and I know why. If I go to setup user preferences and I go to my paths, because I did this at home, but this would not be something you would encounter in the labs, is that I went and did the order of the things. So, and then I don't have these listed here. So sometimes the search order matters there. So let me import that again. It still says completed with errors. You know, I think I'm importing the wrong net lists. Let me go back to, and you see everyone has problems here. Let me actually go to the OneDrive directory, because I know that is where, no, that's not, how do I get there? OneDrive, Cadence, ECE 1000, Allegro. Okay, let me import that way. I was importing the wrong set of netlist files, and so the errors I was getting is I had different footprints, and I was in the wrong location for where my net listing is. So that's why it's important to make sure you're putting them in the correct directory, and so I wasn't. So to finish off this video, we'll go ahead and place all these components. And now when I'm going to place components, notice how that gray thing went to this orange, because that's telling me where to keep it. And now you can also see that, hey, wait, this is a board that's huge compared to what I need it to be. So I'm going to zoom in just even a little bit. And go ahead and place these components. And so those are all the components here. And so they're all placed at this point. Now, in the last video here, we're going to go and show again how to kind of de-rat's nest this and do layout for this. Now, one thing I want to point out here is that notice how all of these are green. The last ones we did, these were yellow, because, or they might also have been green, but they also had yellows. But these are all surface mount components, so there's no holes to drill here. And so we have to route all of this on the top. Now, technically, we could route these to the top here as well. However, typically through-hole components are soldered from the bottom. So I'm going to solder these assuming that I'm soldering them from the bottom. And so we'll talk about that in the next video.